This is problem set number 6, problem 2. Consider a thin rod of length L equals 0.4 meters, coated with charged paint. The total charge Q naught is equal to 1 times 10 to the minus 4 coulombs and is spread uniformly over the rod. Point P sits a distance of B, which is equal to 0.2 meters, from the end of the rod, as shown in the drawing. Part A, what is the rod's linear charge density? Okay, so we have a rod, right? And this rod has, this rod has a certain length that we're going to call length L. Okay? So that's length L, which is equal to 0.4 meters. All right, and then there's a charge on the rod that's distributed evenly. Let's use this. So it's painted with a certain charged paint, right? And that's distributed over the rod evenly, right there. Okay, and that charge is Q naught, which is equal to 1.0 times 10 to the negative 4 coulombs. And again, that charge is a uniform charge on the rod, okay? Then we also have got a certain point up top, right here. And that point is point P. Okay. And point P is a distance of, what is it? 0.2 meters from the top of the rod. Okay. So B equals 0.2 meters. All right. And we have to find out the rod's linear charge density. Okay. Real quick, I'll add a coordinate system so that we can reference what is positive, what is negative, and in which direction. So this is X, and we'll call this Y direction. Okay. So part A, find the linear charge density. All right, well, I'm going to use the formula for linear charge density, right? Linear charge density is equal to the total charge divided by the total length, right? So it's a charge over length will give you the density. And again, the keyword is that this thin rod is uniformly charged, which is given in the problem. Okay, so I'm going to use this formula to find my linear charge density. So what is the total charge of my rod? That's equal to Q naught, right? And the total length is also, in this problem, is also length L, right here. Okay, so I'm going to plug in the values for that. So Q naught is equal to 1 times 10 to the 4, or sorry, times 10 to the negative 4 coulombs. And the length is given in the problem as 0.4 meters. Okay, so if I plug that in my calculator, I'll find that my linear charge density is equal to 0.00025 coulombs per meter. And that will be my answer for part A. Okay. So moving on, let's go to part B. Part B, what is the electric field at point P? So what is the electric field here at point P? Solve symbolically before plugging in the numbers. So there's going to be an electric field at this point, point P, due to this thin rod, right? Because it's charged. Due to this charged rod right here, I'm going to feel a certain electric field at point P. Now we want to know what is that electric field at point P. Okay? So in order to do that, I will use the formula for a line charge, right? That's from chapter 20, section 4. So chapter 20, section 4, we have the formula for a line charge, the electric field due to a line charge, and that's dE is equal to K times dQ over R squared R hat, okay? I'm going to use this formula. So let's look at this a little bit clearer, right? So my thin rod is uniformly charged all throughout here, right? So it doesn't matter if I take a piece of it, a small piece, or I take half of it, or if I take the entire rod, they're all going to have the same charge density, right? Because that just depends on the material. And the problem said that the charge is uniformly spread throughout the thin rod. Okay, so that's going to affect our point P, as mentioned, and it'll have a certain electric field there, right? What direction is the electric field going to go? Remember, we're going to think of this point as a positive charge at point P, right? So what is this positive charge here located at point B? What direction will it go to due to this positively charged rod of 1 times 10 to the minus 4 coulombs? Because they're like charges, this is a positive charge and this is a positive charge. It's going to push it away, right? It's going to repel this point charge right here at point P. So the direction of the electric field, which we can think of as a positive charge point in space here at point P, that is going, I'll use green, that's going directly up. That will be my electric field due to this thin rod with a positive charge, right? And if you notice, this is going straight up along Y. Oops. So it's just going to be my electric field along Y. Right? So it will be my EY. And why is that? Because P is sitting directly above the thin rod right here. So there's no there's no x component of my electric field. It's not like the electric field will push it at an angle or to the right or to the left. That's not the case. There's no angle. It's just going straight up, right? Because if you think about it, this little, let's say we have a little charge here. Okay, so let's take this little piece of the thin rod, right? And let's call this dy, right? This is a little piece of that thin rod of length dy. That little length dy right here is going to have a certain charge, right? So it will be dy with charge dq, a little piece of the charge of that little piece of the thin rod right here. Okay. That is going to have an effect on the point P, right? It will have a certain electric field due to that little piece of our rod. So it will have a certain dE along the y direction, right? So, and again, we'll have to add up all the little dEs that exist in this thin rod. So that plus this little, they all have a certain dE that that point P feels. Okay. So, we're gonna use this formula right here to solve for the total electric field due to these little dEs felt due to these little pieces of the rod. We'll add them up one by one until we get the total electric field. Okay? So let's do that. So I've got dE is equal to k dq over r squared. First, I'm going to find my charge, my little charge dq. Okay, that's due to this only this little piece of dy right here. Oops. Okay. So, a little side quest. So my linear charge density okay, that's lambda, right, is equal to q total over the total length, right? So in other words, q is equal to my charge density times my length, okay? But if we're only talking about this little piece right here, this little piece, right, of the thin rod, because remember, we're going from this end of the rod, we're taking little chunks all the way and keep adding those little chunks all the way until we reach this end of the rod. So we keep taking little chunks. And then eventually we get the total electric field from these little dEs of the pieces, right? So dq, the charge of this little piece of dy, is going to be equal to the charge density times the length, but not the full length of the rod, just this little tiny length dy, right? Okay. So oops, that's going to be called d baby q, which means the charge dq due to this little charge dy. Okay? So we'll plug that in. It will be dE is equal to k lambda dy over r squared. What is r squared right here? What is r squared? R squared right here is r is the distance between charges. Distance between the charges. Okay, so what do I mean by that? That means I'm talking about the distance from here, from P, all the way until this distance. Just imagine this is a little tiny chunk, right? Imagine dy wasn't that big. I had to make it a little big so you could see it. But imagine it was this height dy. So that distance right there is going to be r squared. Okay? So this is the distance between the charges, right? Meaning the distance between this point P and the distance of this little charge I took from this little piece of the thin rod. Okay? But what is that distance? So I could separate that into two, right? This one, we already said B was equal to 0.2 meters. This one we'll call a random variable, we'll call it y. So my distance between the charges, right, r, is going to equal b plus y. Okay? So I'm going to plug that here for r. So dE is equal to k lambda over what it was r. R is b plus y. So b plus y squared. Okay? And then dy. All right? And if I want to find the total electric field, which is for this entire rod, I'm going to have to integrate with little dE's, right? So this little piece of dE plus this little piece of dE plus this little piece of dE plus this, all the way until I reach the end, from the start to the end. Okay? So that's what I'll do. I'll take the integral of dE. I'll take the integral of both sides, right? And then that will give me, and that's, by the way, the integral from 0 to the whole length of the rod, L. Okay? So, I'm going to get the integral of dE is just the electric field, the total electric field E, right? And these are constants, right? K, that's a constant. Lambda, that's a constant because my charge density doesn't change, right? So I'm going to take that out, k lambda, and then that will be the integral of 1 over b plus y squared dy. Okay? So in order to get the integral of this, I'm going to remember the integration rule. So an integral of x to the n power of dx is equal to x and to the power of n plus 1 divided by n plus 1. Okay? As long as n doesn't equal -1. Okay? And in this case, n is equal to -2 and not -1, since 2 is in the power of 2 is in the denominator, so it's -2, right? So if I solve that, I get that is equal to k lambda, and the integral of 1 over b plus y squared dy is b plus y to the power of 2 minus 2, plus 1. Minus 2 plus 1 is -1, all over -1, right? Because -2 plus 1 is just -1, from 0 to L, all right? So I'm going to be left with k lambda, negative k lambda, and then b plus y to the -1 is just 1 over b plus y, right? From 0 to L. Okay, so I'm going to get that's equal to negative k lambda 1 over b plus L minus 1 over b plus 0. All right, and I'm just going to distribute this negative to both terms inside. So I'm going to get that's equal to k lambda times 1 over b minus 1 over b plus L. Okay? And then now I can just plug in the values. All right. The value for K, which K is the electrostatic constant right here, right? Because this is a constant, that's an electrostatic constant. The value for K is, and this is something that you should have in your cheat sheet or remember, it's 8.99 times 10 to the 9 Newton meter squared over Coulomb squared. Okay, that's the value for K. And the value for lambda is solved right here in part A. It's 0.0025 coulombs per meter. Okay. And then we plug in 1 over b. And we said it was given to us that b is 0.2 meters. So 1 over 0.2 meters minus, I'm going to make this a little smaller because I'm running out of space. Minus 1 over b, 0.20 meters, plus L, which was 0.4 meters. Right? And that was L? Yeah. Right here. Okay, so just plug that in your calculator and you would find that the total electric field is equal to 7.49 times 10 to the 6th newtons per coulomb. Okay? But that's just the magnitude of the electric field. Well, it is saying positive, but we can confirm that too, because we know that this whole rod has a positive charge, right? 1 times 10 to the minus 4 coulombs, but it's positive. And this point P, the electric field there, you just imagine there's a positive charge there. A positive plus positive would repel it, so it would push it up towards positive y, right? That's why we have the coordinate system. So we know that it will, the final answer, if we want a vector, right? This is the magnitude, but the vector of electric field is positive 7.49 times 10 to the 6 newtons per coulomb along the j hat direction, okay? Okay, now moving on to part C. So that's our final answer for part B. We found the total electric field, or the electric field at point P, okay? So part C is saying a point charge of Q1, which is equal to a negative 6 times 10 to the minus 7 coulombs is placed at P. What force does it exert on the rod? Okay, so this time, the point charge here at P has a negative value. So now we imagine now this has a negative charge. Okay. Right here, it has a negative 6 times 10 to the minus 7 coulombs. It's placed at point P. What force is it going to exert on the rod? Okay. So we will use our formula also from chapter 20, section 4. Chapter 20, section 4. And that formula is the electric force formula, okay? So the formula for electric force is equal to the point charge Q times the electric field E. All right? So it was given to us. What was our value for the point charge, right? It was negative 6 times 10 to the minus 7 coulombs right here. Oops. Right? That's placed at point P, so it's now here. And then the electric field, we calculated in part B here. So we just multiply them together and we can find the value for the electric force, the force exerted on the rod by this Q, this point charge. All right. So again, these formulas that I write in blue ink, it's something that I think you should have in your cheat sheet or just know it by heart, okay? I'll just write this down. So this is the electric force. This is the point charge. So it's the point charge placed at point P, right? Which had a value of minus 6 times 10 to the negative 7 coulombs. And this is the electric field, not electric, but electric field at point P. Okay? The point charge placed at point P. Okay? So again, we'll just plug that in. So the force is going to be equal to the point charge placed at point P, right here, Q1. So equals Q1, oops. Q1 times E, okay? So Q1, they said, was -6 times 10 to the -7 coulombs. And we multiply that by the electric force at point P, which we solved for in part B. Or not electric force, but electric field at point P. Okay, so that's positive 7.49 times 10 to the 6th Newton per Coulomb. Okay. And if you plug that in the calculator, you're going to get an answer of positive times negative will be negative, right? So it's negative 4.494 newtons, okay? And if we want the force vector, we'll have to add the direction of the force, and that will be, right, we said negative along j hat. Oops, we'll mark that in red. Oh. Okay. And it's easy to see why that would be negative, right? We have this time this positive charged rod and a negative charged point charge. So a positive and negative, that force will come down, right? So because of that, then we exert a negative force along negative y, going towards negative y, okay? So that's our final answer for part C.